Welcome to another session of online causal inference seminar. Today, we are very excited to have Michal Kolesár from Princeton University talking about evaluating counterfactual policies using instruments. We are also excited to have Edward Vytlacil from Yale University. And today's Q&A will be handled by Ying. So let me switch it over to her.
Thank you, Razi. So as usual, please submit your questions in the Q&A section for us to track them more easily. It's at the bottom of the Zoom window. So today we have the collaborator of the speaker, Jonathan Ross, to answer questions during the talk. We'll also raise some questions to the speaker during the talk when they stop for the questions. So I encourage you to submit your question as soon as you have them, instead of waiting for us to ask for questions. So without further ado, the stage is yours.
Thank you so much, everybody, for coming. This is a joint project with John Roth and Pepe Montiel-Olea. Let me share my screen. Can everybody see it? Yeah. So this project is called Evaluating Counterfactual Policies Using Instruments. So the motivation, oops, now I can't see my screen anymore. The motivation for this talk is sort of the fact that often in applied economics, people use instrumental variables, and as sort of the most one of the popular applications these days is this so-called judge design, where people exploit the fact that the judge that you're assigned to is essentially random, and then by the virtue of being assigned a more lenient judge, maybe I'll get a lighter sentence. But if I was assigned a more strict judge, I may get a harsher sentence, and then I can use this quasi-random variation to figure out what's the causal effect of, say, sentencing on some outcome like recidivism. And this is a very popular design. These judges that I'm assigned to don't have to be judges. They could be, sort of, people have applied this in many other settings. They could be patent examiners, child welfare investigators, prosecutors, doctors, and so on. But the key feature in these designs is that there's typically many of these judges. And so there's when I'm thinking about what is the causal effect of being assigned to these different judges, there's different comparisons that we could be making, and the standard thing people report in practice is just the two-stage least squares estimator, which aggregates these cross-judge effects together. Or sometimes when they people get a heterogeneity, they also report something like the marginal treatment effect curve. But this approach has two problems. The first one is that in order to interpret the two-stage least squares estimator as a weighted average of local average treatment effects, you need an IV monotonicity assumption, which the IV monotonicity assumption just says that, well, if I'm assigned to a more lenient judge, and I'm not released, say, then I'm also not going to be released if I'm assigned to any of the judges who are a bit less lenient. So in other words, if a judge is more lenient on average, the judge must be lenient, in fact, on every case. But now we have institutional knowledge and both statistical tests that suggest that this assumption is a little bit too strong, at least in this scenario. And the other issue with these designs is that even if we believe monotonicity, it's not exactly clear how policy relevant this two-stage least squares estimator is, because oftentimes the reason people look at these designs is that they're interested in other types of policies, such as, for example, encouragements to release more defendants, so giving judges directives to be more lenient. And so it's not entirely clear what exactly is the connection between the effect of such a policy and this weighted average of local average treatment effects that the two-stage least squares estimator is getting us. Now, there are both of these critiques have been recognized before, so there's been a lot of effort in trying to weaken the monotonicity assumption while still preserving a causal interpretation for the estimator. But of course, this doesn't address the second issue, and as so Ed has this nice eloquent quote that I'm giving here that sort of raises this, that effectively, ideally, you try and write down what your policy of interest is first, and then try and figure out what's the right estimator for it, rather than writing down the estimator first and then hoping that it's relevant for the policy at hand. And one way how to get directly at the policy at hand is to use this marginal treatment effects framework. However, in order to sort of directly use it, you need this assumption of policy invariance, which essentially says that, well, if I'm asking, say, the judges to be as lenient as the most lenient judge, that's my policy, what's going to happen under this counterfactual is everybody's going to be making exactly those decisions as the most lenient judge. But that may not be reasonable for two reasons. One is that, well, first of all, that also requires monotonicity, but even if monotonicity holds, it may be that the policy changes the internal ranking of the judges. If I'm giving them an algorithmic decision, algorithmic recommendation saying, well, actually, this defendant is not a high risk, you should release them, maybe they'll change their internal ranking of the defendants. And so what we do in this paper is three things. The first one is just a fairly simple thing, which is that we set up a framework that makes this policy evaluation explicit. So we're going to think of the policy as essentially another instrumental variable. It's just that in the data that we have, its distribution is degenerate. I never see the policy. But you could imagine a data set where I did observe the policy variation. And in this case, you can think of the policy as an instrument in the sense that it's going to affect the treatments, and then it may affect the outcome then through the treatment as well. And so what we observe in the data is just the treatment assignments without the policy, with only quasi-random variation in the judge assignment. And what I would like to know is what are the outcomes under this policy where I observe the counterfactual policy assignment. And with this framework at hand, what we'll then do is to derive a characterization of the identified set of the policy effect. In general, this is going to be the policy effect is not going to be point verified, but it's going to be a set. And we're going to give a characterization in terms of a linear program. And sort of the idea here is going to be that this program is going to be very scalable, even if you have a large number of judges. So it's going to scale linearly with the number of judges. So it's not going to, the linear programming problem is not going to blow up the way we set it up. And then we're going to ask, well, okay, I have this linear programming characterization of the identified set. In the baseline, I don't need any monotonicity or policy invariance assumptions. Without imposing any extra assumptions, only using the quasi-experimental variation of the judges, this identified set may be pretty large. So that's going to raise a question of maybe we can impose some extra assumptions that may help tighten the identified set. And so we're going to ask a question, what types of assumptions are going to be useful? And we'll actually show that for many policies, IV monotonicity is not going to be useful for tightening the identified set. In fact, we'll show that if you apply it naively, in the sense that you sort of pretend that monotonicity holds in the data, but is actually rejected in the data, you may end up with either an empty set, so that would be the better case, but otherwise, if you apply it naively, you may end up with a set that's actually larger than the tight identified set. And so the way I think about it is that for many types of policies, IV monotonicity is going to be neither necessary nor sufficient for policy evaluation, even though, of course, it's crucial for interpreting the two-stage least squares estimand in a causal way. And so instead of worrying about monotonicity, we'll try and think about what are other types of restrictions that help us tighten the identified set. And we'll think about sort of restrictions that are sort of have the flavor of relaxing the policy invariance assumption, which in some cases actually would give us point identification. But so we'll be able to sort of bridge this gap between imposing policy invariance, which we think is too strong, versus imposing nothing, which may not get us very much in terms of informativeness of the identified set. So I think hopefully that was clear. If there are no other questions, I can jump into the setup.
Yep, there are no questions. Thank you for asking.
Okay. So we're going to observe an outcome y and a binary treatment. So throughout the talk, I'll use this judge example as a running example. So you can think of the outcome as, say, in the simplest case, a binary outcome, whether the defendant commits crime. Treatment is whether they're released or not, maybe by the judge. There's going to be a multivariate instrument, so there's going to be many judges I am going to be assigned to. And there's going to be these potential treatments. As I said, I'm going to index them both as by the judge that you're assigned to and by the policy. In the data, I'll always see a equal to 0, and I'll be interested in what happens when a equals to 1. So in the data, what I observe is the judge assignment, the treatment that corresponds to the potential treatment without the policy, and the observed outcome is the potential outcome under the factual treatment. And what I'm going to be interested in is this parameter theta, which is the average counterfactual outcome. So that's the potential outcome that under the counterfactual treatment regime. And throughout, I'll assume this instrument independence assumption that the instrument is independent of both the potential treatments and the potential outcomes. And this, of course, embeds both random assignment assumption and the exclusion restriction that the instrument and the treatment only affect the outcomes. That the instrument and the policy both only affect the outcomes through their effect on the treatment. So there is no direct effect. Now, with this setup, I can just define the identified set as follows. So I have these observed data. They follow some distribution P that I can identify. But the model primitive is the joint distribution of the potential treatments and potential outcomes, which I'm going to call P star. And I'm going to say P star generates P if P star is compatible with the observed data. And then the identified set for theta is just going to consist of all the average outcomes under the counterfactual policy such that I can find some P star that is going to be in the set of possible models that I'm considering such that P star generates P so that it's compatible with the observed data. And now, of course, the name of the game is going to be, what types of restrictions we put on the collection of potential models. If I put more restrictions on the set of possible models, I'm going to get a tighter identified set. But what are the reasonable restrictions? So I think it's going to be, for our purposes, useful to distinguish between two types of restrictions, which one is just a restriction on the what I'm going to call the marginals. And I use the word marginals here because it's going to look at those are restrictions that restrict the potential outcomes and potential treatments, but these restrictions only involve one judge at a time. So there's no cross-judge restrictions that of the nature that say, well, if the most lenient judge releases the defendant, then also any of the less lenient judges would release them. So those types of restrictions I'm going to call cross-instrument restrictions because they involve the joint distribution of all the potential treatment assignments. So for example, policy implementation details will typically imply restrictions on the first stage marginals. So for example, a quota would say that the average release rate of each judge under the counterfactual must be at least 20% or something like that. But that doesn't involve restrictions on the joint distribution. So what we will make use of is in most of our analysis is this policy monotonicity assumption, which is sort of similar to an IV monotonicity in the sense in the following sense, which is that it says that everybody who's released currently would also be released in the counterfactual. So if I think of the policy as some encouragement, the policy has this, and if I think of the policy as this instrument, it's just that I don't observe variation in the instrument. But if I did, it would satisfy this monotonicity assumption. So by Vytlacil's equivalence result, you can think of that as follows. So there is some latent model for if there's some latent model for determining whether I'm released or not, and there under this assumption there must be some latent variables, some cutoffs VZ that each judge uses for determining whether I'm released or not. And what the policy A does, it only increases the threshold. It doesn't affect the ranking of the judge. That may often be plausible, for example, if if the policy is some directive to be more lenient. In contrast, the IV monotonicity assumption of Imbens and Gangres is a cross-instrument assumption. It says that if a judge Z is more lenient, then Z prime on average, in this average sense of expectations, then it must be lenient for every case. And again, this is equivalent to a latent index model, but here the rankings for all judges are common across judges. So the judges don't disagree on the rankings of the defendant. That may often be too strong in applications. The third type of restrictions you may want to impose is called policy invariance. So this is the assumption that the Heckman and Vytlacil's baseline framework imposes, which says that, in fact, the ranking V that judges have is the same across all the judges, and it's the same under the status quo and the counterfactual. And the only thing that the counterfactual does is just simply increases the threshold. And you can know, by this equivalence, you may know that policy invariance implies both of the previous assumptions. So it's going to be a strong assumption. One way to see that it's a strong assumption is that if you think of both the policy and the instrument as a sort of a collection of multi-dimensional instruments, then policy invariance says that this multi-dimensional instrument satisfies IV monotonicity, but there have been recent work by Mockstead, Torgovitsky, Walters, and also in some original arguments in Heckman and Vytlacil's work that argues that this is a strong assumption because it imposes implausibly strong homogeneity restriction. So that's those are the types of restrictions we'll consider. And let me pause for questions if
there are
any.
no active questions.
Okay,
But
so
we encourage speakers to submit questions if you have them. Thank you again for asking.
okay, so with this setup, let me give you two main theoretical results that we have. So the first main result is going to just give a tractable characterization of the identified set under this setup. So recall that we're interested in this average outcome under the counterfactual. So this is just the definition of the identified set. So I need to find a data generating process for the potential outcomes that matches the observed data. And so how do I do it? Well, one thing you could do is, and this is what people have done before. So for example, Toru Kitagawa's paper, or this recent paper by Ed and his co-authors, is that you enumerate all the possible types. So what would I be sentenced if I'm assigned to Judge A, Judge B, Judge C? If there's 3 judges, that gives me 8 types, and then I also have to consider what would happen to me under the policies and not. So if there's 3 judges and a policy, that would give me 2 to the 4 types. So we may call this compliance types based on the values of these potential treatments. And then you just enumerate all the potential compliance types, and then the observed data distribution is going to be a mixture of of the distribution for these different types. But of course, if Z takes on many values, then there's going to be many types. So if you do the calculation, if I have 50 judges, there's going to be more than 10 to the 30 types. So this is not going to be tractable to do in settings where you have a reasonable number of judges. So what we're going to do is we're going to give a characterization where instead of the problem scaling exponentially with the number of types, the problem is just going to scale linearly. And so how can we do this? Well, the key insight is that actually the parameter of interest and the data, they don't involve any cross-judge restrictions. Right, so I only ever observe for each individual being assigned to one judge, and the counterfactual parameter is just, again, involves only assignment to one judge at a time. And so for that reason, it's going to be just sufficient to look at these marginals where I look at the potential outcomes under assignment to one judge at a time. So I don't need to I don't need to consider the joint distribution of assignment to multiple judges at once. I just need to consider these marginals because this is the observed data. That observed data involves only these marginals, and the parameter of interest, the counterfactual, the average counterfactual outcome under the policy, again only involves these marginals, and not the joint distribution of what happens to me if I'm assigned to judge A and judge B at once. And so to find the identified set, I just need to search over these types of marginals that are consistent with the data, but that's going to scale linearly with the number of judges, so it's going to be doable. So here's the first main result of the paper is that is just formalizing this intuition. What I need to do is with discrete outcomes, I can just characterize these marginals in terms of these probabilities that I'm going to call pi. So this is if I'm assigned to judge Z, what is my treatment under the counterfactual? What is my treatment under the no policy? And what are my potential outcomes? And then I can marginalize these further. So if I just want to say, look at one potential outcome and one assignment, I'll use this notation. So I'm going to conjecture some of these some marginals. And then I'm going to say, well, there exists a distribution P star that is consistent with these conjectured marginals if pi agrees with the data, so I can explain the data. So this is just a set of linear restrictions. And if these marginals imply the same joint distribution of the potential outcomes, that's the only way that these marginals are connected. And then finally, I'll just need to make sure that the pi's are some valid probabilities and some non-negative and are sum to 1. So without sort of further restrictions on pi star or on P star, this is all you need to check whether this joint distribution can characterize is compatible with the data. So the only restriction across these marginals is just that they have to give you the same distribution of the potential outcome. So that makes it easy to obtain sharp bounds using linear programming because the parameter of interest is linear in these probabilities. So I have a parameter of interest that's linear in the probabilities. All the restrictions I gave you are linear. And so I just, and the scale of the program is linear in the number of judges. So it's very fast to do it. In our applications, it's basically instant. So that's the first result. It's also easy to do inference here because this is a linear program. There's many papers that consider inference on parameters that are identified by linear programs. So I guess all of them were published in 2023. We are going to do the simplest possible thing, which is just projection. We're going to find an identified set for the, sorry, excuse me. We're going to do projection, which is we're going to find a confidence set for the data probabilities. So we're just going to construct a confidence band, and then we're going to project it down to the parameter of interest. And in our application, it turns out that's actually pretty, it works pretty well. Now, after you have this characterization, in many cases, it may give you an identified set, which is quite wide. So you may ask, well, what are the other restrictions I can impose? And our second main result is going to say that actually the IV monotonicity type restrictions, if you impose them alone without any other further restrictions, they will not help you tighten the identified set. So on the other hand, in some cases, policy invariance may help, but in cases where it's too strong, you may not want to introduce it. So what we're going to do instead is introduce a relaxation of policy invariance. So to give you some intuition for why IV monotonicity doesn't help, let me give you the simplest possible example, because the result essentially just generalizes this example. So consider the case where if I'm not released, I cannot commit crime. So I can only commit crime when I'm released. So I know what happens. I know that y0 is always 0. The question is just what happens to me if I'm released? What's y1? And suppose that the counterfactual policy of interest is I'm going to release everybody. So I'm not going to hold everybody in pretrial detention. So then the counterfactual parameter of interest is just y1, the average y1. And because under the counterfactual, I'm releasing everybody, policy monotonicity, so saying that if I'm releasing anybody right now, I would also be releasing them under counterfactual, it holds automatically. And suppose that I don't make any other restrictions on the model. Then it turns out that the linear program has a very simple solution. The identified set is just going to look at each judge, and it's going to say, well, what's the lower bound for the identified set? Well, I'm interested in the average value of y1. So that average value has to be bigger than the probability that I commit crime and that I'm released if I'm assigned to a particular judge. And it also has, right, because this is a joint probability of y1 equal to 1 and dz equal to 1. So this joint probability has to be smaller than the marginal probability that the y1 is equal to 1. And similarly, I can use an analogous argument for an upper bound. And now the key is that these bounds for the identified set, they hold for each judge. So to get a shared bound, I just intersect all of these bounds across judges. So let me now, so that's what the sharp characterization is. What is the characterization under IV monotonicity? Well, under IV monotonicity, I know that for the policy of releasing everybody, the most informative judge to look at is always just the judge that's the most lenient, because everybody less lenient has less information on the people who are released, because all of those less lenient judges, they agree on the release. They agree with the most lenient judge on who should not be released. So in that case, I don't actually take an intersection over all of the judges. I just look at the identified set, looking at the most lenient judge. And so what's the upshot of this? Well, if IV monotonicity is not rejected by the data, then it's going to be the case in the population that whether I'm intersecting or these one judge at a time bounds or not, doesn't matter. They're going to give me the same thing as if I'm only looking at the most lenient judge. So the identified set is going to be the same if IV monotonicity is not rejected. But if it is rejected, then intersecting these bounds is going to give me something smaller than this bound that only looks at the most lenient judge. And so in general, our linear programming characterization is going to give you bounds that are tighter than the naive bounds from sort of imposing monotonicity. On the other hand, IV monotonicity here is not going to help you tighten the bounds. And now the intuition for why it doesn't help you, why is it the case that that imposing monotonicity doesn't help you tighten the bounds is just that if all the judges, if you impose monotonicity, all of those judges who are not released by the most lenient judge are always never takers. And so for those, we only have trivial bounds for what would happen to them if they're released. On the other hand, if monotonicity is rejected, some of those guys are defiers with respect to the most lenient judge, and there's going to be some information in the data about what would happen to them if they're released, because some of the other judges may be releasing them. And so in this sense, the monotonicity assumption is the least favorable in the sense that it implies that there's least amount of information in the data about what are the potential values of y1. Now, we can generalize this simple example a little bit and in the following sense. So suppose that the only restrictions on the model I am imposing are restrictions on the first stage marginals. So what are the release rates under counterfactual and so on, but I'm not making any cross-judge restrictions. And I impose that either I know the outcome if I'm not released, or my policy is sufficiently strong so that under the counterfactual, everybody who's currently released by the most lenient judge would also would be released under the counterfactual, no matter what other judge they're assigned to. So releasing everybody is a special case of this, but this is a little bit weaker than that, and incorporates policies such as eliminating some of the judge discretion. And then the result still holds true, in particular, that if the data doesn't reject IV monotonicity, the identified set for theta doesn't depend on whether you impose it or not. On the other hand, if the data is, if IV monotonicity is rejected, then the bounds, depending on how you construct them, are going to be either wider or empty. So let me pause for questions at this point.
Hi, Michal. There have been some questions, but have been answered by Jonathan. I think Hito also have some questions, but as a panelist, he cannot write in the Q&A section.
Okay.
Hito, do you want to speak up?
Sure. So can you hear me?
Yeah.
Okay. Yeah. So this is all very interesting. So I was putting some questions in the chat, but so does this suggest anything sort of about particular types of information that would actually be very valuable? So that it's kind of interesting to see that these monotonicity assumptions that in some cases may actually be very plausible, and we may have things to say about them, are not very helpful, but other things that would actually be very valuable that we could possibly know in some cases or get information about.
Yeah, I think that's a good question, and I think where I'm gonna go next. So in some cases, policy invariance would be very valuable because so the simplest case is, suppose that I'm gonna ask everybody to release as many people as the most lenient judge. If I impose policy invariance, well, then I'm point identified because I just look at what is the outcome under assignment to the most lenient judge. So that's one type of restriction that actually is going to be very helpful. And the difference between again, difference between just IV monotonicity and policy invariance is that IV monotonicity doesn't restrict at all what happens under the counterfactual. It just restricts what happens to assignment under different judges, but they're all in the absence of the policy. With policy invariance, you're making these counterfactual restrictions. So for this particular policy, yeah, you're going to be point identified if the policy is I'm going to ask everybody to release as many people as the most lenient judge. But that may be a bit too strong. You may not think that every judge is now going to be making the same decisions as the most lenient judge under the policy. And so one thing we do next is we are going to consider relaxations of that to help us tighten the bounds.
Thanks.
Yeah.
One more question, kind of about the beginning, the way you set it up with this being interested in this policy that you don't actually see yet in the data. At some level, seems very similar to the way you could think about external validity, where you kind of see data from one setting and you're interested in data in a different context. Is there any connection? Is this a useful way kind of to frame questions about external validity as well? And maybe the functions could transfer to that setting?
I think that's an excellent point. That's precisely what we're doing here. So I guess questions about counterfactuals are questions about external validity. It's just a particular type of external validity. I think it'd be interesting. I think we found it very helpful in sort of clarifying our thinking and setting it up in this way, where we think of, potentially I could observe the variation in the policy, and so I'm going to sort of set it up as if there potentially could be variation. It's just that in the data I don't have any variation. And then I'm going to think about what are the restrictions that are reasonable to impose on the counterfactual variation that are going to help me that are going to have informational content. I think it'll be interesting to consider this in other settings, not just this particular setting. But yeah, we haven't thought through it. But yeah, I think the idea is more general. That's a good point. Now, I guess this was the question that Hito already previewed, which is when can other types of restrictions help, and when is it IV monotonicity and when is it other restrictions if IV monotonicity is not helpful? So in the characterization I gave you, there are sort of two sufficient conditions that ensure that IV monotonicity doesn't help. You can also construct counterfactuals where IV monotonicity helps. I'm not going to go into that. I'm going to sort of focus more on the on what are other types of restrictions other than IV monotonicity that are going to be helpful. So one of them is this policy invariance restriction, and the example of that is this quota example that I just gave. If you impose policy invariance, you're point identified in this quota example where I ask everybody to be releasing as many people as the most lenient judge, because under policy invariance, everybody would be making exactly the same decisions as the most lenient judge currently is making. And so I just have to look at what's the outcome for the most lenient judge, and I'll say that's going to be the counterfactual outcome. So that's the point identification result. Now, without imposing policy invariance, the identified set will be an interval, and it may be a trivial interval in the following sense. So suppose that the most lenient judge is not releasing that many people, say 20% of people. And so there's going to be a lot of people who I never see released in the data set. And so, in particular, I will not know whether their treatment effect is +1 or -1 for those people. Some of those people I'll see that they're not released and not committing crime if they're not released, but some of them maybe I see are committing crime that are released. So there's going to be a bunch of people in the data set that I never see released, and that may have treatment effects of +1 or -1. And if I ask the other judges to be as lenient as the most lenient one, the trivial bounds are going to say, well, I'm just going to take those guys, but I'm only going to take all those guys with treatment effect +1, and I'm going to release those. And that's going to be allowed without any further restrictions on the counterfactual. Similarly, to get the lower bound on the policy, I'm going to say well, what the less lenient judges are going to do, they're going to take all the guys who are never currently released, who have a treatment effect of -1. I'm going to release those. So the slope of the counterfactual is going to be +1 on and -1. And so in this sense the bounds are trivial in the sense that as I move from the data further out, the NFAT set's going to just keep growing. And the model is not really beyond pinning down where the data is. It's not going to help me narrow down the identified set. So one thing we could do is we could try and think about why this is implausible. Well, in this example, I'm allowing the judges to disagree completely with one another. It may be that I don't believe that imposing that they agree exactly on the ranking is plausible, but maybe they agree approximately. How can I sort of formalize that? One way you could formalize it is that I'm going to bound the disagreement rate. And so this is what we're going to do in the empirical application. I'm just going to say, if I'm currently released by the most lenient judge, there's going to be some probability, at least some probability 1 minus delta, that I'm also going to be released when I look at judges who are less lenient. And so this just says that there's almost a fraction delta of individuals that disagree with, on which the less lenient judges disagree with the judge who is most lenient. I think this is a nice restriction because we actually have some evidence on disagreement among judges that can help us calibrate this delta. And furthermore, it's simple to incorporate this type of restriction into our identified set. So let me show you how to close the talk. Let me show you our empirical application where you so that you get some sense of sort of how informative these types of restrictions are.
Sorry,
So
Michal, for the interruption. Just to let you know, you have maybe 4 minutes to give Edward enough time for his discussion.
Yeah,
Thank
yeah,
you.
no, so I'm going to take 4 minutes to just walk through the application.
Thanks.
So we're going to take this application from this QJE paper by Egan et al., where the random assignment is an assignment to prosecutors, and those prosecutors decide whether to pursue charges against defendants or drop the charges. Here, if you do a test for IV monotonicity, it's rejected. And so our discussion here is going to be irrelevant. We're going to consider two types of counterfactuals. One is eliminating prosecutorial discretion. So I'm going to not allow the prosecutors to drop charges. And I'm going to ask what would happen if I just prosecute everyone. And the second is going to be the opposite of that. I'm going to consider quota where I require all prosecutors to drop at least as many charges as the most lenient one. And the most lenient one in this case, their non-prosecution rate is about 16%. We're going to, just to make things simple, I'm going to look at only the prosecutors that have a lot of cases. So I'm going to look at the 10 prosecutors with the most cases, and all of them have about 2,000 cases or more. So this is what the raw data looks like. I'm just plotting the non-prosecution rate of different judges. So this is Judge 278. This is the most lenient judge, or prosecutor rather. They don't prosecute it about 16% of the time, and their average outcome is about 28%. So if I'm assigned to this prosecutor, the probability that I commit crime is about 28%. And you can see from this figure that monotonicity is rejected because these two prosecutors, 308 and 342, have very similar release rates, but very different outcomes. So it can be that they're releasing the same types of people. Now, if I ask what's the identified set without imposing any monotonicity or policy invariance for this counterfactual where I eliminate prosecutorial discretion and I require that the prosecutors prosecute everyone, it's actually fairly tight. It's between 35 and 36% with a fairly tight confidence interval. And actually much tighter than the bounds I would have gotten if I just look at the most strict prosecutor. Why is this? Well, it's just that, as I was explaining before, what the sharp identified set does, it looks at bounds that take one prosecutor at a time and then intersects them. So in this case, the intersection is given by this orange line. So I get a pretty tight identified set. The lower bound is determined by Judge 342 and the upper bound by this Judge 682. If I imposed IV monotonicity, I would only be looking at the strictest prosecutor, 682, and I would get a much wider identified set. So this is a sense in which imposing IV monotonicity is not helpful in this data, and if you apply naively, you actually get wider bounds. Let me close with our second example, which is this quota to release as many people as the most lenient judge. Here's what the results look like. If I don't impose anything else, I get a fairly wide identified set for what would happen. Again, that just comes from the fact that there's many people who are not released. And so if I don't impose restrictions on who the judges are allowed to release, there's many things that could happen. And then in here on the x-axis, I'm plotting the bound of the disagreement rate delta. You can see that once I impose that the disagreement rate is, say, at most 20%, I can actually rule out. So this is the current outcome is currently about 33% of the people in the data set commit crime. If I impose a tight enough disagreement bound, I can actually conclude that under this policy where I require the prosecutors to be more lenient, I would improve outcomes, so the crime rate would go down, at least according to the point estimate of the sharp identified, so the confidence intervals are a bit wider. So I think I'm out of time, so let me just thank you.
Thanks, Michal, for the great talk. There are currently no active questions, so maybe we can just directly go to Edward for the questions, but I encourage the audience to ask their questions in the Q&A and we can come to them at the end.
One, excuse me. Let me pull up my slides. So I thought it was a fabulous paper. I know oftentimes panelists, discussants say that without meaning it, but I mean it. I really like the paper. I'm going to give some background from my perspective to fit it in the literature, not very differently from how Michal did anyway. I'm going to briefly talk about late analysis, mostly studying the framework to how it compares to what was just done, briefly talk about MTE analysis, mostly to compare it to what was just done, and then discuss the what was just done within that context. So as everyone knows, I feel silly saying this in front of Guido, given that this is him. Late analysis compared to classical IV imposes different assumptions. It's weaker and allows for treatment effect heterogeneity or equivalently random coefficients, but at the same time is stronger by imposing instrument monotonicity, or in other words, a first stage model. So classical IV, there's no first stage model, but very strong assumption on the outcome. In comparison here, no assumption really on the outcome, but there is some assumption. It's implicitly a first stage model that may not hold for judges. Then what's the point of this? Well, you do two-stage least squares and you get a causal interpretation when you would not without the monotonicity assumption. And in particular, you get the average effect for subgroups defined by how they respond to the instrument. Of course, is that policy relevant? It depends on if there's a connection between the policy and how people are responding to the instrument. If the policy affects the same people as the instrument, then you're great, you're exactly policy relevant. Or if it's close, maybe you're close. If it's far off, then it does not seem very helpful. Foreshadowing, of course, what we just saw, if one could define the instrument specifically to be the effect of the policy or correspond to the policy, then this would be perfect. But in general, if the instrument doesn't correspond to the policy, it still has a causal interpretation, but doesn't necessarily have a policy interpretation. Within that set of assumptions, you could ask about other parameters besides the late kind of parameters. And as was discussed, one obvious parameter to look at is the average treatment effect. And a classic result, originally in Bloch and Pearl, is that for that parameter, imposing the late monotonicity assumption does not help reduce the width of the bounds compared to exogeneity alone, provided that the data is consistent with the assumptions. Okay. Another thing you could do, say with a multi-valued treatment, is think about generalizations of late. So for example, effect of treatment A versus treatment B for those who would select in treatment A if encouraged to A, but would select in treatment B if encouraged to B. And for those kinds of parameters, of course, generalizations of late, naturally monotonicity plays a key role. Do any of these parameters correspond to a policy effect? Well, average treatment effect does if it's a really extreme policy. The straight conditional effects do if the policy is acting upon people who are, again, acting as if they're responding to the instrument. Different framework. You could say equivalent, or you could say different. My work with Jim, marginal treatment effect and policy relevant treatment effect. And so there, we're imposing a selection model, which is equivalent to the late monotonicity assumption. But by imposing it as a selection model, that allows us, for better or for worse, to define a richer set of parameters and to incorporate other functional form restrictions. If I say for better or for worse, I think obviously it's for the better. That's my preference. If you're more of a traditional Rubin causal model person, you might view this as a bug of the framework, that you're defining parameters that you don't think should be defined given the variation in Z. Oops, I went backwards. So within this context, we consider what we call policy relevant treatment effects, which is a treatment parameter explicitly defined to answer a given policy question. The kinds of policies we look at are policies that encourage or discourage some treatment. So kind of in the same way that the Z is encouraging or discouraging going into treatment, we're looking at policies that encourage or discourage going into treatment. We relate the policy changes to changes in the latent index of the selection model, and then proceed that way. So in the end result, we partially identify or partially identify the policy parameter through kind of connecting as much as we can variation in response to the instrument to variation how people we think would respond to the policy change. So getting into this paper, the framework looks exactly like the late framework, except they're defining an instrument that exactly corresponds to the policy change. And so in a way that makes late immediately policy relevant. If late is done with a binary instrument that exactly corresponds to the policy change, then late is the effect of the policy. And typically you just take the instrument as given. Here they're not taking this instrument as given, they're just defining it to be the effect of the policy. And so then in some ways you're golden. Obviously the problem, the reason it's partially identified, is in the data, the policy is not yet in effect. Well, under the counterfactual, the policy would be in effect. So unlike standard late, it's a partially identified parameter, not a point identified parameter. They're going to impose late monotonicity on this instrument being the policy shift, not on the other instruments. And why do they kind of do that? I mean, they're not interested in the effect of treatment for people who would select treatment at one value of the instrument, but not at some other value of the instrument, except for responding to this instrument A, the policy change. So I think I just said this. So in their analysis, at least their base analysis, they're not defining parameters that look like late types of parameters or late kinds of types. So there's no type for would selecting the treatment if assigned to one judge, but would not selecting the treatment if assigned to some other judge. They don't need to do that for two reasons. One reason that no parameter they're looking at relates to those groups. They're looking at a parameter defined by what would be the effect of being of the policy versus not the policy, A0 versus 1, not looking at effects for these other subgroups. And they're not imposing any connection between effects for these other subgroups and the effect of the policy in the main analysis. So it's going to be somewhat similar in spirit to the policy relevant treatment effect, in that they're defining explicitly a parameter that explicitly is the effect of the policy. It's dissimilar to policy relevant treatment effect, and that they're not, at least in the primary analysis, they're not imposing or exploiting a connection between the policy variation and variation in response to the other instruments. So then one thing that they do that ends up happening, which I think is actually really nice, and at least a little bit to me was unexpected, is the policy effect parameter, given the way they represent the latent probabilities, is linear in the latent probabilities. And so typically in this kind of Blocky and Perl style setup, or in my work with Bai, Zim, and Sarah, for an unconditional parameter, like the average treatment effect, the linear program ends up being linear in the latent probabilities. But for a conditional parameter, like average effect conditional on some subgroup, it only ends up being linear in the latent probabilities if the probability of that conditioning event is known or is point identified. And so I would have thought that trying to study effect of the policy the way they're doing it would not result in a linear program, because probability of being influenced by the policy change is not point identified. But for them, it ends up being a linear program because they're changing the definition of the linear probabilities by representing the policy change as an instrument. And with that change in the definition, change in the framework, everything ends up being linear. The parameter ends up being linear in latent probabilities, not linear the way I would have thought it would end up being. Then they can just do a linear program. So I thought that was really nice. It's lower dimensional than I might have thought it would be, because, again, they're not defining these subtypes for, they're not defining probabilities for events like I would select a treatment at one value of Z, but not for some other value of Z. They don't need to, because that can be any parameter that depends upon that, and the parameter doesn't relate to that. I think I already said this. So just summarizing, I really enjoyed the paper. I thought the setup was really clever. This idea of taking the policy and representing the policy as an instrument and imposing late monotonicity on that instrument, the policy, is clever. I've never seen that before. I would not have a priori thought that would work very well. I wouldn't have thought that would necessarily give you good results, but it does. And I think that was interesting and somewhat surprising. I like the fact that it ends up still being this linear program, where, again, it was not immediately obvious to me that you would get a linear program, but it is because of the way they set up the latent probabilities. It seems especially appropriate for this judge design context. I mean, there's some trade-offs versus conventional late analysis or versus policy relevant treatment effect analysis. So, for example, for PRTE, you might, for better or for worse, to impose some functional form restrictions on the marginal treatment effect, which helps if you believe the restrictions that you're imposing. It facilitates leveraging variation, responsive variation to Z, the variation in response to the policy, if you believe that's valid to do, which Michal argued very persuasively it might not be in this context. Final thought I wanted to give, I do think, maybe not here, but I do think in general, there is some value to imposing monotonicity in Z, even when it has no identifying power for the parameter of interest, if you strongly believe the assumption. Because then if you reject it, you know that you're rejecting the exogeneity assumption. So try to say that a little bit better. Testing exogeneity alone is very difficult in this kind of framework, this kind of context. Testing monotonicity and exogeneity is easier. It's easier to reject. And it's easier to reject exogeneity if exogeneity is false, if you're additionally imposing monotonicity. So not in this context, because in this context, it seems like we really believe exogeneity and don't believe monotonicity. In some other context, if you really believe monotonicity but were unsure of exogeneity, it would completely make sense to impose monotonicity in order to be able to test the exogeneity assumption better. And again, I really enjoyed the paper.
Thank you, Edward, for the insightful discussion. We are a little bit short on time, but Michal and Jonathan, do you want to briefly respond, maybe engage in the discussion?
Yeah, well, thank you, Ed, for such a lovely discussion. I think it was nice how you put things in perspective. I think with respect to your last point, I completely agree that in the paper we take the stand that I take exogeneity as given, and then I ask, when I'm looking at the data, I'm asking, is there support for these other assumptions? An alternative interpretation in some settings where monotonicity is rejected is that it's not really the monotonicity that we're testing, it's this joint assumption of exogeneity and monotonicity, and in those cases it's useful to do these monotonicity tests if you interpret them in this way, that they're joint tests of monotonicity and exogeneity, and if I reject, that's an evidence against the exogeneity assumption. I think we should sort of that's gonna what the right interpretation is gonna be is gonna depend on context, but yeah, we have not we're taking here the exogeneity is given. That may not be a great sort of a great thing in some applications. And with respect to I guess you mentioned this one advantage of the MT framework is that you can impose restrictions on the, say, MT functions to help you with identifying power. I think I agree that that's once you relax that framework and go to these disagreement bounds, you can't quite do that because, or at least I can't think of quickly of an easy way of doing that. It's possible to incorporate some outcome restrictions on our in our setup. So for example, you could impose restrictions that y1 is bigger than y0 or y1 is bigger than y0 for some groups and still incorporate that. Some sort of monotone treatment response type restrictions. But yeah, I guess all frameworks have their trade-offs, and so this is one, but it's not the only one.
Great. Thank you so much again for the great talk and the very great discussion. It's probably a good time to wrap up. Let me share my slide. Okay, so next week we'll have Corwin Ziegler from Brown University, who will be talking about causal health impacts of power plant emission controls on the modeled and uncertain physical process interference. And we will have Frederick Xavier as our discussant. And we hope to see you next week as well. Thank you so much.